All right, good evening, everyone. This is Jeremy Carty, Kopernik educator here, and I'm here to introduce the program tonight. I just wanted to point out a few things on our website, some possibilities for donation that you can either donate through the video description. We have our classic Streamlabs link. You can donate live during the stream here. But I'm going to show you some other methods that you can support us as we head into the winter. So our website is kopernik.org. You can, of course, go there for the latest news about our programs. So this is our Black Holes on Black Friday tonight. So quite appropriate. We're going to be learning about black holes. We have our Kopernik educator, Roy Williams, who you'll meet in just a few moments. And then we have a couple of other events here. One is Giving Tuesday, which is on Tuesday, December 1st, so this coming Tuesday. And that's an opportunity to donate to Kopernik and other nonprofit organizations. It's handled through Facebook, and you can log in and see the link, the donation link, as early as Monday, just before midnight. But the key here is if you donate as close to 8 a.m. on that Tuesday, December 1st, as possible, Facebook will double all those donations within that time frame. And I think it's up to, once it reaches 7 million donations, it cuts off. They won't match anymore. So that's a great opportunity and a great option for supporting Kopernik Observatory and Science Center. And then also just in general, we have our year-end donation. You can see that on our website as well. But Giving Tuesday is the big one, so look out for that this coming week. One other way you can support Kopernik is also on our website. You can see Amazon Smile here. And it's a big holidays, big buying season, so you can actually support Kopernik. A small percentage of what you purchase will
cost them nothing.
Okay, and it costs you nothing, yep. So it's 0.5% of your purchase will be donated to Kopernik at no cost to you. Alrighty, so last thing I want to point out on our website here is the clear sky chart. As you know, we've been doing a bunch of observing live streams in the past. Now, we've had some pretty bad weather lately, so that's why you haven't seen me in a while. Just there hasn't been a great opportunity. So November didn't work out for our deep sky stream. Hopefully December we'll have better luck with that. We did get the 14-inch up and running with our with that camera I've been using for the 6-inch, like on the moon, for instance. So that one's working well, and we were actually able to image the Orion Nebula M42 with pretty impressive clarity. It's a little bit of a big object for the 14-inch though, so we'll probably choose some smaller deep sky objects out there, like the Ring Nebula or something around that size. Okay, so you can go to Clear Sky Chart though to see some of the latest weather here at Kopernik. So the cloud cover, the seeing, the transparency, those all come into play. The darker colors, darker blue rather, is a sign of good or little cloud cover, you could say. And then the transparency and seeing, the darker those are, the better planetary views you're going to get, the better deep sky objects you're going to get. Right now we're sort of heading in to full moon this month and into December. So deep skies are going to be hard to get. But mid-December, hopefully we'll have some good skies. And also the Jupiter and Saturn conjunction is coming up on December 21st. And if we have clear skies, we will be streaming that to you. So be on the lookout on our website for more information about that event and stay up to date on the weather conditions, because we're excited. Keep our fingers crossed for it. Okay, so I have a little clip here to sort of set the scene for our program tonight. This was a recording of the solar eclipse back in 2017. So we'll click on over to that. We'll run through this for a few minutes, and then we'll pass it over to Roy for his program. All right.
Weather worked out, right? Oh, you got my computer. That's it. Wow. The weather really lucked out.
Oh, wait, 1 second.
Roy, what an amazing have to do that, can you? I know. Now they're not around, so. But we got 1 minute. What do you think? Yeah, someone get a picture of that. Here it comes. Here it comes. Here comes the shadow.
Oh my God, it is.
Look how weird it's getting. Everybody get in there. Everyone get with their cameras. Hey, Nicole, can you put your camera in there? This is for Roy. Everyone put their camera in so it's in my view. It doesn't matter. Wow. Okay.
Oh my God, it's getting so dark. Oh, holy cow.
Here we go. Oh!
Oh, there it goes.
Solar filter off. All right, kids, inside.
Peter.
Whoa.
Holy cow, take your time. Mom, look up without your glasses. Oh my God.
Oh my God.
My God.
All right. Get that camera going now.
Wow.
There's the corona. I hear the cricket. Okay, look to the right. That's Venus. Venus to the right.
Yeah.
Jupiter should be. Don't see it yet, but there's.
Oh my God.
There's
This is wild.
Oh, did no one torn?
I think they have it coming. That is
Did it look? Oh, that's great. Good eye. Good eye. It looks so three-dimensional.
It does. Unfortunately, the camera doesn't really. Seems like it's nighttime. Anybody else's camera catching it? No. No, it's like a still sun. You can't zoom in and out together. No. Look at the cricket.
Look at the horizon. You can see sunsets and like lots of different. Right. The red.
Oh, I got it.
Different places. There goes
Okay,
there's
put
the
your
bees.
glasses back on.
Okay,
huh?
glasses back on.
Put the glasses back on.
Really?
Yes.
That was quick. That seemed less than 2 minutes. Holy cow. Wow, it's like a torch coming on.
All right, you're up.
Okay, welcome to Black Holes on Black Friday. That was me and some friends down in Tennessee there watching the solar eclipse 3 years ago, and I got to tell you, it's fantastic. If you ever get to see a total solar eclipse, we got one coming up in 2024 that's going to run through Buffalo, Rochester, up toward the Adirondacks, and it kind of ties in with this show because we're going to talk about solar eclipses and what you can actually observe them, and it kind of proves something about gravity. So that's why we kind of showed that. So, okay, to get started now on a little slideshow, Black Holes on Black Friday. I think this is like our 10th year in a row we've done this. So Drew called me up and asked me, hey, do you want to do it? It would have to be virtual. I said, yeah, we have to do it because we got to just keep doing this. So it's an anniversary. It's an annual thing that we just have to do. All right. So anyway, so starting the slideshow here. So black holes, the ghosts of our universe.
Might need to click.
You
should be good.
Okay, could be good now? Okay, great. Okay. So to first start off, we have to talk about star formations, how stars form, because it's the larger stars that become black holes. And here is part of the Eagle Nebula here. This is taken from the Hubble Space Telescope, and you can see that this light is causing the gas to glow. Ultraviolet light is causing the different gases in this nebula. Hydrogen and helium gas is glowing due to the ultraviolet light. And you can see these little islands out here, these little peninsulas sticking out. These are these globules of where stars are forming. And so this is a birth of stars, star formation. And what you got is hydrogen gas is collapsing down and forming stars in here. So we call those protostars when they first start out, before there's really any nuclear fusion. So you get the contraction of gas and dust due to gravity, and it's like a snowball effect. The more mass you have, the more it's going to gather in, the more gravity it has. So it's going to give you that type of snowball effect. When you reach about 15 million degrees, that's when you get something called nuclear fusion, and that's when you officially have a star. Okay, so basically at that point, electrons are stripped off their parent atoms, creating a plasma. A plasma is a gas that's electrically charged, and we see that in the sun. That's what the sun is made out of, the fourth state of matter, plasma. And it's releasing a great deal of energy. Okay, energy, nuclear fusion is way more, provides way more energy than any other type of like chemical process and so forth. All right. So basically you have a balance between outward pressure of these nuclear explosions going off and the balance and gravity pulling inward. I got a diagram coming up that will show that. So when is a star a star? So basically when you have four hydrogens coming together to form helium, it produces some energy. This actually occurs in a three-step process, what's called a proton-proton chain. But a star forming is considered to be a true star when nuclear fusion takes place in its core. And that's when you're getting it. Basically what we're talking about is creating a new element. You're taking hydrogen, and under great pressure it's fusing it into helium. And however, there's a little bit of missing mass there, and that missing mass turns into the energy. All right. Our sun has different layers in it, and all stars, we're assuming, have this type of stratified layer, with the core being the hottest, and different zones in it until you get the convective zone and sunspots, which are magnetic storms that are on stars on the sun. And the outer layer is called the photosphere, which is what we see with our eyes. But anyway, this nuclear fusion is going on, and basically you're turning hydrogen into helium. And if you were to weigh the hydrogen before it turns into helium, the hydrogen actually ends up weighing more than the helium that you make, and so that missing mass turns into energy. And that's what Einstein's equation is all about. E equals mc squared means that mass can turn into energy. So that missing mass actually becomes the energy, and it works for stars as well as nuclear bombs. So new stars come in a variety of colors. All right, they go from blue to red. I'm going to show you a chart called the Hertzsprung-Russell diagram that will kind of explain the different spectra of stars, the different colors of stars. And it's all really based on surface temperature. It's opposite of your bathtub. The hotter the star, the more blue it is. Okay, red stars are actually cooler. All right. And one of the surprising things we'll talk about tonight is that the more massive stars actually have shorter lifespans. Due to that pressure, they're going to burn through their fuel. Their nuclear fusion occurs a lot quicker. And so even though they have more fuel, it burns through it a lot quicker, and they're a lot hotter too. Okay, they have a shorter lifespan. So the more massive the star, the shorter it lasts. So here's the Hertzsprung-Russell diagram. On the left is luminosity and suns. So you got one sun brightness right here. So this is brightness, basically, if you want to talk about it. And one sun. So our sun is right here. We're a yellow star. We're about 5,000, just below 6,000 degrees. What's weird about this chart is that it increases the temperature down here at the bottom. This is temperature. The temperature at the bottom increases from left to right, so that's kind of weird. So the Hertzsprung-Russell diagram is temperature down here at the bottom and how bright it is on the side. And when you plot stars, they end up making this really nice line here called the main sequence. And it just turns out the main sequence is where stars live most of their lives. Most of the period of time is spent on the main sequence. And then they'll venture off this and become, like our sun will become a giant and so forth. We'll talk about that in a little bit. But anyway, this is how all the different colors we're talking about. So cooler stars are red, and then you have orange and then yellow. and then you get more into the blue stars are higher temperature. So stars, after millions to billions of years, there's no hydrogen. It's burned through, it's fused all the hydrogen to helium, and then helium start making other elements. And that's really what the amazing thing is that it will make up all the way up to iron on the periodic table. And then that's when the stars are going to explode, and then they release other elements to the universe. And so we're really made of stardust. That's what Carl Sagan meant by that, is that stars had to go through this life cycle in order for more complicated elements to be made. So as far as we know, there's no life forms that are hydrogen and helium. So you really had to have some star birth going and star death before you started having life. But anyway, without the outward pressure generated from these reactions, the outer layer of the stars begin to collapse inward, generating new heat, all right, and counteracts the force of gravity. The outer layers of the star are now pushed outward. The star expands larger and larger. So basically what's going to happen to our sun is it's going to run out of fuel in about 4 billion years, and it's not going to supernova, but it's going to expand out to a red giant, and it's going to swallow up Mercury, swallow up Venus, and get close to the Earth. It's going to burn away our atmosphere, and then it's going to puff away into what we call a planetary nebula. And I'll show you some pictures of those planetary nebulas in just a little bit. But here's that pressure we're talking about. So stars are kept on that main sequence by being balanced. It's a balance of outward pressure from the explosions, from the nuclear explosions, so to speak, and gravity pulling downward toward the center. So that balance occurs for most of its lifetime, and that's when it's living on the main sequence. So just to give you a comparison of some of the things we're talking about, here's our sun compared to maybe what's called a red giant, and of course the Earth is very small. So one of the things it does, we need to talk about, is that different amounts of mass will actually warp what we call space-time. So Albert Einstein came up with this idea that there are 4 dimensions. You know, there's the 3 dimensions we're used to, which we call space, and then there's the 4th dimension called time. And he considered it to be space-time, the fabric of the universe. And this diagram here shows space-time. So gravity deforms space-time. So what we're talking about here is that space-time, as mentioned by Albert Einstein, is the never-ending fabric of the universe. The fabric bends around objects due to its gravity. So the more gravity you have, we call this something called a gravity well. All right, so a low-mass star won't bend space-time too much, but a more supermassive star will bend it even more. And of course, as we talk about black holes, it's very extreme how much it bends space-time. And we'll talk about the effects as you get closer toward these objects, what happens to time in space and so forth. So I got a demonstration over here that I think we're going to do here. Let me just see what my next slide is. And yeah, so what we have here is so Arthur Eddington, a British astronomer in 1919, wanted to prove Einstein's theory of relativity. In order to do that, the best way to do that with the equipment at the time was to observe a solar eclipse. And that's why I showed you that video of us down in Tennessee watching a solar eclipse. And he actually, I think he made a first attempt during World War I, but was stopped by the Germans, and they stopped him. They thought they were suspicious of him. One of the European countries, I forgot which. But then later on in 1919, he was able to pull it off an island off the coast of West Africa. And basically what we're talking about, what Einstein's theory predicts, is that as starlight, so right here, here's the starlight, from Earth, the star looks like it's right here, okay? But reality is the path of the star is actually behind the sun, and the path of the light gets bent. So in this case, the shortest path is not always a straight line. So let me show you a little demonstration over here. We have a little model of this, and here is our space-time and our fabric of space-time. You can see I put a heavy object in there, and it warps space a little bit. But if I put even a heavier object, it's going to warp it even more. All right. As opposed to, let's say, just a marble. I don't even know if you'll see it. Probably not. No. Okay. So we'll put the big steel ball there, and that can represent our sun. And then just like the diagram I just showed you, can you go back to the diagram?
Yes.
Yeah. So going back to that diagram real quick. So what we're going to do is I'm going to demonstrate that light from a star. Watch the marble as it rolls past the sun, what happens. So here we go. So, all right, so here, try number one. We're going to roll the marble, and you see how it bends? So it actually deflects, is probably a better word. It deflects. So starlight from behind the sun. So the Earth is over here, let's say, and we're observing the star, and it's actually behind the sun. And normally we wouldn't be able to see this because the glare of the sun is so bright. But at totality, in 1919, the sun and the moon were traveling through a star cluster called the Hades star cluster. So there was lots of stars to see. So it was a good time to take a picture. Anyway, here's what it looks like. Whoops, no, it hit the star, hit the sun. And there we go. So that's the deflection. All right. So that kind of shows the deflection there. And so anyway, Arthur Eddington was able to pull this off with very primitive technology. And in 1919, actually put Einstein on the map, really, because a lot of people didn't really know who he was, believe it or not. I mean, we know him today,
Just click on it.
hold on, click. Okay, there we go. All right. But here's what we're talking about here is very small, precise, extremely difficult measurement for what they had at the time. The equipment they had at the time, they barely pulled it off. But here's totality here. So at that moment, stars start to become visible. If you remember the video I just showed you at the beginning, you could hear me talking about there's Venus. So you could see some stars during the totality. This is the outer atmosphere of the sun called the corona. And these are some of the stars in the Hades star cluster. And they should just be a tiny bit over. I mean, it's not much. Basically, it's the type of precision we're talking about is if you took a quarter about 2 miles away, that's about the angle. That's about the angular difference we're talking about here. So they just were able to pull it off and help prove Einstein's theory. So, all right. So general relativity was first time it was empirically proven, so to speak. So Einstein describes gravity as the deformation of space-time around massive objects. Before that was Newton. Newton thought of it as two objects being pulled together by gravity, and this is a more fundamental way of looking at it. And then a neutron star is even a more dense star, and you can see it how it's pulling more and more on making that what we call a gravity well. Now you can see why they call it a gravity well, because it keeps going down just like a well. Neutron stars, I've got a diagram on that. I'll show you what those are in just a second here. Yeah, here it is. So basically just a life cycle of a star. You have a stellar nebula where stars are formed, just like the Eagle Nebula I showed you in the beginning. You have two routes, basically. The lightweight guys like our sun, very stable for 6 billion years, 7 billion years, something like that. And then it becomes a red giant. Okay, we expect about 4 billion years from now our sun's going to turn into the red giant and swallow up those planets, Mercury and Venus. And then it's going to puff away its outer layers and become what's called a planetary nebula. Now the word planetary nebula is kind of an archaic word. The telescopes back then in the 1700s when this term came about, these objects look like planets, so they call them planetary nebulas. So it has nothing to do with planets. But anyway, we've just kept the term. In the center of these planetary nebulas are typically white dwarf stars. These are very small stars. They're very hot though. They're extremely hot, but they're very small. So and it's the size that makes them dim. So think of it as being a very small. Even though it's very hot, it should be bright, but its surface area is not very large, so it's not that bright. Okay, and then so then you got a middle, or the more massive stars will turn into a super red giant, and then instead of this puffing away the outer layers and this kind of slow dying type of process, a very violent supernova occurs, and that's when you can get the middle guys, the guys that are more in the middle, the middle stars will turn more into what are called neutron stars. This is where all the electrons are stripped, and it's just everything is just all neutrons and compacted, extremely dense, In fact, like a teaspoon of this would weigh like almost like the size of the Earth or something like that. It's just very dense. This matter is, we've never seen matter like this. It's so dense. I think they say the density of a white dwarf, or like a teaspoon, is like the weight of a battleship or something like that. Some incredible amount of mass, of gravity. And then finally, you have the really big stars, 10 times more massive than the sun. I've heard different numbers, 5 to 10 times more massive. Those can turn into black holes. Okay, so that's basically what it's all about. So again, it ties into mass. Not only does the length of the star, the mass determine the lifetime of a star, it also determines where it's going to end up here at the end of its life. Okay, unless it interacts with some other star, which can happen. But okay, so getting into black holes. So they're intense gravitational fields left when a star collapses. Do you have any questions by any chance? Or you've been answering them?
No.
Okay. Yeah, if you have any questions, just go to the chat room and shoot me a question. Jeremy's monitoring the chat room. So how many people we got on?
43.
Okay. All right. So anyway, these stars have to be much larger than the sun. All right. We talked about the star's life cycle, and that diagram, that classic diagram I just showed you, shows that, and it's all tied in with where these objects end up. Okay, so gravity becomes so big that it compresses, forming a black hole. So when I was growing up in high school, black holes were really theoretical, and there were some X-ray sources that astronomers were looking at, but it was nothing really proven on this. Let's see. Let's talk about, so before we get to black holes, let me show you those planetary nebulas. I got some good pictures of that. So here's some of the planetary nebulas with the white dwarf in the center there, the burned out star basically. And here's another beautiful one there. I'm forgetting the name of that one. But so the core of the star is all that remains after the planetary nebula is formed. Okay, very hot, size of the Earth, known as a white dwarf. So imagine a star shrinking down to the size of the Earth. That's why it's so dense. Okay. White dwarfs form if a star has less than 8 solar masses. And here's some more. Here's the Ring Nebula. We get this in all the time, particularly in the fall in our telescopes. We love the Ring Nebula. And they call this the Eye of God in the National Enquirer or something like that. Anyway. I forgot what they call that one. This is the Ant Nebula, I think. So they come up with all these cute names of these things. All right, so anyway, so what we get here is, even for a black hole, we get more and more massive star collapses and forms. You can see this disk around it. So the question is, can you see a black hole? Well, the problem is, at some point you cross the event horizon, and that's the magical line where no matter what, you can't escape. So you really don't see the black hole. What you see is matter swirling down into the black hole, and you'll also see typically these X-ray jets. We see galaxies that are called radioactive galaxies, where stars or jets are shooting out of them, and typically that's at a right angle to the disk here of the black hole. So this material is being sucked down like a whirlpool, and it's bumping and it's energizing, ionizing the gas, and it's creating a magnetic field which is causing this jet to occur. And I think what I want to show you next is, so here's a black hole that's devouring a nearby star. So that can happen as well. Okay. And so you must be wondering about your socks. So where do socks go? People think there's black holes inside your dryer. That is true. There are black holes inside your dryer, but they don't go anywhere. They actually just turn into Tupperware lids because you got extra Tupperware lids. You're joking, right? You're laughing, right? Okay. So anyway, so let me show you a demonstration here on our little device to show you a black hole, what it kind of looks like. So we talked about. So here's a star, and then you got gravity And then, so we can go into orbit around that. So here's a planet going around the star. All right. Here's another planet. And another one. So you can see it. Whoops, got thrown out of the solar system. All right. So as we get more and more gravity, it's going to get more and more difficult to escape. So if you were to pull down on this, and you get, see how those marbles bang together? That's that matter getting sucked into the black hole. All right. So just imagine it going down to it would actually be going down to like a fine point, to a what we call a singularity, to a single point. So where you're approaching infinite, you're approaching zero volume. So basically, we're seeing really indirect evidence of black holes for the most part. So as that material goes down, what we call the accretion disk, particularly if there's a nearby star that's getting some of its material sucked into it, you'll see those X-ray jets coming out. So that was really the first idea. Was that astronomers noticed there's all these X-ray sources. There was one in Cygnus called Cygnus X1, and that was a prime candidate for a black hole. And then we also noticed there's a lot of X-ray sources in the center of galaxies. All right, but more recently we've been able to. So when a black hole devours a star, it emits radiation detected by X-ray telescopes. So here's our black hole I was talking about. So imagine if I could pull that down even further, if I could pull that fabric down further until it got down to a single tiny point, that would be your black hole. And there's some imaginary line here, wherever it is, it's called the event horizon, where not even light could escape. I suppose there's and then if you have mass, there's probably another line out here where your spaceship, if you're in a spaceship, you wouldn't want to get too close because you'd get sucked in too. But that would be further out. But here gives you an idea. Let's say if we're on a planet and we throw up a ball, it does this parabolic arc type of thing, right? So we can throw up a ball, okay? So and then you go to the next planet and it's more massive, and so you throw it up with the same force and it only goes up so high. And then finally you're on an even more massive planet and it barely gets above your head type of thing, all right? And then if the gravity pull is much, even for light cannot escape, it would be this. So if you're on a black hole and you had a flashlight, the light would do something like this, okay? So looking at this concept again, so like a regular star, light's going to leave no problem. It's going to basically go out in a straight line for the most part from the surface of the star. And then a neutron star has so much gravity that the light is going to bend as it leaves the star, goes out in a curved path, and maybe a more massive neutron star might start going around. Finally, you reach a black hole. So this is kind of showing you the spectrum. As you increase your gravity, you're going to get to a point where not even light could leave that surface, so to speak. So that's another way of visualizing what we're talking about. So this is our Milky Way galaxy. Obviously, it's not a real picture because we haven't sent a spacecraft out there, but here is our sun is supposed to be right here. So this is an artist's conception. We live in what's called a barred spiral galaxy. There's a little bar running through it. And we live in the Orion arm of the Milky Way galaxy. And right in the center here is a supermassive black hole. All right? So, and let's see, I think I got a video on that. And I'm wondering, yeah, I got a video coming up. So yeah, there's a supermassive black hole in the center of our galaxy. And let me show you, what we've been able to do is we've been able to take photographs of stars as they go, they're in actual orbit around. So again, we can't see the black hole itself, but you can actually see these stars going around it, all right? So let me see, I think I forgot to get this booted up, so I'm gonna have to search for it online, yeah. So help me out, Jeremy, let's see. So I gotta go to YouTube. So, whoops, what did I do? So folks, hang with us in a second here.
It's on YouTube?
Yeah, so you just search
go
for, thanks.
Okay.
So I forgot to get prepared here, sorry. It won't take long. So, let's see. Forgot this. I thought I had the link. yeah, here we go. Let's see. Yeah, here we go. So am I on? I don't.
There we go.
Okay.
Yeah,
They didn't hear me at all?
No, I don't think since the video.
Okay, were people saying that?
Yeah. Yep.
So, okay.
Right,
So let me go back and do that. I heard you guys weren't hearing me. So anyway, basically what we got here is we were able to look in toward the center of the Milky Way galaxy, and we were able to see these stars that are just whipping around this black hole. And we're able to calculate, from that, we're able to calculate, here are the stars. Now this is an animation taken from our observations to clean it up a little bit, make it look better. But you can see that these things are in crazy elliptical orbits, all right? And that they're moving at great speeds. So anyway, from this, we can figure out the mass of the stars. We can also figure out how big the black hole is. And there's the black hole. So the black hole's been identified in that location. So again, this is kind of indirect observation because we're not really seeing the black hole. We're seeing these stars go around the black hole. Now I'm going to go back to my slideshow and continue on from there. So now let's look at a picture.
I think we have to fix it.
So now they can still hear me though, right?
Yep.
So now we're going to get let's try to get a real image of a black hole, or at least the closest thing we've been able to get. And we can do that with a radio telescope. So there's an array of radio telescopes all around the world that is called the Event Horizon Telescope. And a couple of years ago, in 2017, they were able to take this picture of the black hole in the galaxy called M87. M87 is 55 million light years away, so it's just outside of what we call the local group. So it's kind of in our neighborhood. This black hole is equal to 6.5 billion masses of the solar masses, so it's a big one. And yeah, so this galaxy has a X-ray jet shooting out of it, just like we talked about, and it's obviously coming from this black hole. So this is what we call, technically, this is a series of radio images put together. So that's probably your closest thing you could call as a direct observation of a black hole. And here's the jet. Here's M87 in Virgo, and here is that jet shooting out of that black hole that you can see. So it's a very, what we call an energetic galaxy, M87. So, and the event horizon is the point at which once you cross that line, you cannot escape. And Chandra was the mathematician who calculated this, and it's really not that complicated formula. I'm sure it's complicated to derive, but the radius, the distance from the black hole, is equal to twice g. G is what's called the gravitational constant, and it's one of those variables. There's about, I don't know, 20 variables in the universe that we don't know why they're set at those numbers, but G is one of them, big G, and then the mass of the black hole itself, and the speed of light is another one of those variables. We don't know why the speed of light is the speed that it is, but the square of that is, you divide that into that will give you the radius. So it's a very clean looking formula. And what's amazing, some of these basic rules like E equals MC square and this are just so basic formulas. So, but getting to them is very difficult mathematics. So journey to the center of a black hole. According to Einstein, gravity bends time and space-time. And once you pass through the event horizon, there is no going back. All right, so there's different theories. You're going to get stretched because maybe if you're driving your spaceship and your feet are in the front, and they say that your feet are closer to the black hole, it's going to cause you to get pulled like spaghetti. I don't know if I believe that, but anyway, that's what they tell you. Black holes will spit you out the other side of the universe. That's a myth. All right, people had the idea that there was these things called white holes. If matter goes in there, it's going to come out the other side somewhere else. That sounds like my sock theory. So, fact, once you're in, there's no getting out. So, some people theorize our universe might be inside a black hole. That might be a possibility. Okay. Any questions on the chat room?
I don't see any.
You've been answering pretty good, or?
No, I haven't had any super specific ones.
Okay.
So.
All right. And so let's talk about another aspect of Einstein. Einstein talked about that speed slows down in space depending upon what you're doing. If you're traveling really fast or if you're traveling near a strong gravity force, your time will slow down relative to the Earth. So you'd be traveling along in your spaceship and 15 seconds might go by on your spaceship, but on the other second spaceship further out, further away from the black hole, maybe 50 seconds went by. And this has also been proven. We sent one of our crews that went to the moon on the Apollo spacecraft, had atomic clocks on board, and they lost a few nanoseconds, a few billionths of a second, because they were traveling at great speeds. So, so this is another aspect of Einstein that's been kind of proven. So time slows down the closer you get to the black hole relative to the Earth. Okay, so it's a relative type of thing. And so that's pretty much it. So, you know, if there's any questions, that was my last slide to remind me to do the demo, but we already did the demo. Yeah. So yeah. Do we have any questions online about black holes? I'll take your questions. So, how are we doing?
Yeah, we're good. If anyone wants to see the black hole simulator,
yeah, we can do that again. Ooh, okay, here we go. So, back to the black hole simulator. So, let me show you. Well, it's more than a black hole simulator. We call it that, but we do all types of things with it. Yep. And the idea is that we use it a lot to show orbits. That's really the main thing. And the other thing so I showed you like the orbits of the orbit of a planet going around like this. So Newton thought of gravity as being like, imagine if you had a ball on a string and you're whipping it around, and that string represents gravity. Whereas Einstein thinks of it as being space and time in this fabric, like this. The curvature of that is causing us to go around in orbit. Now the other thing I can show you is that how do planets form? So you have these things called planetesimals. Here's our protostar in the center, and you have these things called planetesimals, and there's one that's a little bit bigger there. Maybe that will do something. Some of this is kind of random, so watch what happens as I toss them in there and watch what happens. Here we go. I haven't done it with this small one, so I hope this is our smaller version of this. It should work. So you see how they're grouping together? So you'll watch some of the marbles will actually group together. That's where a planet would form. So just by chance, some of the marbles will just like form together in a group. Whoops. They left the solar system there. So here we go. Let's try again. So let me try again. All right. Yeah, see how they're bunching together right there? So yeah, so that would be a planet forming. So you can kind of show that idea of planets forming. So okay, so that kind of ends the show.
I think we have a couple of
questions. Oh, we do. Got some questions. Go for it.
So David asks, why do some, but not all black holes, even supermassive black holes, have jets emitting from them?
Oh, okay. Why do some but not all?
Yes.
Oh, okay. Well, from what I've read on that is that it has to do with as that accretion disk forms, that it becomes electrified and creates a magnetic field. So maybe some of those fields are weaker and they have to become twisted or something. That's what I found out in the reading. And they do typically shoot out at 90 degrees to the to the accretion disk, which is a lot of things in magnetism sees that. If you take physics and you know about the left hand rule and so forth, it seems the things seem to work in right angles. So that's what kind of that reminds me of that. But I haven't really have heard that there was. But my gut feeling is maybe that magnetic field isn't forming.
Okay.
So.
Let's see. Cindy, I can't quite the METE. I'm not sure if that was a typo in your question, but if you want to retype your question, I'm not sure what the mete is. in that
Read me what was
it says. Can you explain what causes the METE from a black hole? I don't recognize that. It might just
be a typo from
a
neutron star from a black hole. Wouldn't be that.
Yeah, I'm not sure.
Okay.
But yeah, if you just want to rephrase or just inform us on what you mean, for sure.
I can see it right up here, right? Is that it?
Yeah, it should.
Okay.
It should come up. Yep.
Okay.
You want to? Yeah, Philip has a question there. If you want.
Philip, okay. The one. What determines why a supergiant produces either a black hole or a neutron star? So it's all just mass. It's just at some point. I'm not sure what the numbers are exactly because I've seen different numbers, but it's anywhere from 5 to 10 solar masses is the range where that middle ground is. I think once you get above 10, it's going to collapse more into a black hole, and then if it's somewhere, so it's all about the mass. So.
And Cindy, I think, has rephrased the question.
Okay, good.
Yep.
How can they be sure that the stellar evolution theories are true since the only star we see as closely as the sun? Oh, well, we see many stars out there. So we see stars in all different, we see them in stellar nurseries forming. We see them when they're on the main sequence all over the place. So it is true our sun is the most closest. That is true. Our sun is the closest star, so we can examine it. Like I don't know if it's really been confirmed that there are sunspots on other stars, but I mean, our sun has them. So there are problems like that. Like how do we know if there's our star spots? But no, we see stars in all different stages from all around us. Yeah, so red giants to. So that's the idea there. Mm-hmm. Does that make sense?
Yeah.
What else we got?
Cindy, she meant jets when she was trying to.
Jets.
Explain the jets more.
Oh, that previous question. How can they be sure that? Okay. How can we explain the jets? Jets. Oh, I see jets. So basically, what we got going on is that the material getting sucked into the black hole is becoming highly energized, and when it does, it creates electric field, and electric fields are tight, and when you have moving electric fields, you're going to get magnetism. You're going to get a magnetic field forming, and so that field is perpendicular to that disk, and that's what causes the shooting of the X-rays through that magnetic field. Tough questions. These are good. Okay.
Black holes are complex. I think that's what we have so far.
Yeah. Okay.
So if you want to.
So let's kind of close. I just want to tell you, really get to see the total eclipse coming up. I know talking about this 4 years away. It seems like a million years away, but definitely check it out. And don't forget, we do have a link. If you enjoyed this show, we do have a PayPal link at the bottom if you'd like to donate. And Jeremy's got these. You cross your fingers and check the clear sky clock for these upcoming live streams that we're going to observing live streams that are going to be happening. So we're going to keep the programming going until we get things going back up here live at Kopernik. And again, amazing Tuesday. And Amazon Smile. By the way, with Amazon Smile, you have to have smile.amazon. It's a little tricky. I've done it a couple times. Your computer might want you to go back to the Amazon where you normally shop, but you have to put smile.amazon. And again, it doesn't cost you anything. And if you were to buy something big, what's the percentage again? Is it 0.5%? 0.5%. So if you buy anything really huge, please do it. That'd be fantastic because it doesn't cost you anything. Okay. Anything else?
Nicholas actually reminded
Oh,
me of
no.
something, so I'll jump
Okay, go
in
ahead. Go
here.
ahead. Okay, folks, thanks a lot for having me, and Jeremy will conclude. Thank you.
Hello again. I hope you all enjoyed the show. Let me bring the camera up. There we go. Oh yeah, I guess I could take my mask off.
What's Nick saying?
Nicholas Gaidash, one of our educators here at Kopernik, pointed out that there are sunspots on the sun, something we've been monitoring through the Astronomical Society and such.
Right.
And I did want to gauge people's thoughts on maybe doing a solar stream at some point.
You mean right now there's sunspots? I know a
Yeah,
couple weeks ago there's
there's
right
some
now.
more coming.
Well,
Yep.
tell people how rare that is right now.
Yeah, if you know the solar cycle, it's an 11-year cycle of peaks and troughs. So we're not quite at the peak yet. We still have a little ways to go for that. So it's sort of rare to get spots at this point in the solar cycle. So if we can find those and image them, it might be possible to do a solar stream. So if you're interested in that, let us know. You can let us know right now and through chat, or you can message us on Facebook.
Oh, so he's telling you there's star spots. Okay.
Yep. So maybe I was maybe you reminded me different way here. Star spots on.
Yeah. So I thought there
Okay.
were, but I wasn't totally sure. But I thought people had spotted those.
Okay. Yeah. Yep.
It seems like there would be.
Yep. On Betelgeuse. Yep.
Oh, Betelgeuse.
That's
okay.
what he's saying.
Oh,
as
that's
well,
cool.
yep.
Okay.
Okay. So yeah, then I guess we'll wrap things up. Stay tuned for Giving Tuesday there if you'd like to support us through donation. Again, that 8 a.m. time is the best time to donate, but we'll be running that event all day on Facebook, and the Facebook link is in the video description. Okay, so we will see you next time, hopefully in the next observing stream. Bye, guys.